Okay, let's dive right into this. Imagine you're walking into a high-stakes system design interview for a massive tech company. And look, they aren't asking you to build some simple web app. No, they want you to build the invisible nervous system that controls exactly how and when new code actually goes live. Today, our explainer is going to tackle one of the absolute most fascinating architectural challenges out there, designing a large-scale feature flag system as a service provider. We're going to distill some truly incredible engineering practices, drawing heavily from platforms like Databricks, to show you exactly how to ace this specific challenge. So here's the prompt your interviewer just wrote up on the whiteboard. Design a feature flag system handling 300 million evaluations per second. I mean, just let that sink in for a second. We're not talking about a simple true-false toggle and a local config file here. We're talking about completely decoupling code deployment from feature enablement at a scale where a single tiny bottleneck could literally take down an entire global infrastructure. The tension in this kind of architecture is huge. We need absolute control, blistering speed, and flawless reliability all at once. So here's our whiteboard game plan. 1. Setting the constraints. 2. The smart switchboard architecture. 3. Building the management brain. 4. Zippy the pipeline. And finally, 5. Security and risk. All right, starting with Section 1, Setting the System Constraints. Drawing straight from Databricks' internal safe system, our very first constraint is throughput, 300 million. That is the sheer volume of feature flag evaluations our system has to handle every single second during peak load. Think about it. Every time a user logs in, every time an API is called, every time one microservice talks to another, they are all asking our system, hey, should I run the new code or the old code? Next up is latency, 10 microseconds. And notice I didn't say milliseconds, microseconds. Because feature flag checks sit right in the hot path of the core application, any delay compounds instantly. If our system takes even a little too long to answer that new code or old code question, we slow down the entire customer experience. So 10 microseconds is our absolute hard ceiling for P95 latency. And finally, we have propagation delay, 3 to 5 minutes. When a product manager clicks turn on for a new feature, or an on-call engineer hits a panic kill switch to mitigate an active incident, that configuration change has to propagate globally to all services within just 3 to 5 minutes. Moving on to Section 2, the smart switchboard architecture. To kind of ground this highly complex distributed system, we're going to use the smart switchboard analogy. A smart switchboard relies on a layered approach. See, we don't want a massive monolithic brain trying to micromanage every single connection in real time. That'd be a disaster. Instead, the rules are defined centrally. That's the brain. Then, those rules are delivered asynchronously down a pipeline. And finally, the actual decision, the evaluation itself, happens deterministically right at the local switch, embedded directly within the microservices themselves. Now, what's really interesting about this architectural choice is the why behind it. Why local evaluation? Well, if we used a centralized evaluation model, every single service would have to make a network call over the internet to our flag service just to check a flag. Remember that 10 microsecond speed limit we just talked about? Yeah, a standard network call takes milliseconds. It would immediately fail our constraints and create a massive single point of failure. So instead, we use local evaluation. We pass the flag configs down to a local SDK running inside the app. The app just checks its own local cached memory. 0 network calls. Boom. Instant evaluation. Let's look at Section 3, Building the Management Brain. This is our centralized control plane. It's where our rules and logic are actually created and stored. This brain holds vital metadata, starting with the flag key, which is just the string identifier used in the code. It holds our targeting rules, like only enable this for users in Europe or only for beta testers. It also manages rollout strategies, whether that's a simple Boolean on-off switch, a complex multivariate A/B test, or a percentage rollout. And speaking of percentage rollouts, the brain is what manages deterministic bucketing. It hashes a user's ID with a seed to assign them a bucket from 0 to 99. This is absolutely crucial because it safely and consistently routes, say, 25% of users to a new feature, ensuring the same user always gets the exact same experience. Oh, and of course, it mandates strict audit logging. We need to know who changed what and exactly when they did it. The brain also categorizes our entire inventory of flags. As Martin Fowler points out, not all flags are created equal, right? We've got release toggles for gradually rolling out new features. We have experiment toggles for A/B testing, where we absolutely need stable, statistically valid routing. We've got ops toggles or kill switches, which are basically emergency tools to instantly degrade non-vital functionality if the system is under heavy load. And finally, permissioning toggles to control things like premium or alpha tester features. Managing this inventory efficiently is key, so the whole system doesn't just collapse under its own complexity.
All right, Section 4, Zippy the delivery pipeline. Okay, so now that the brain has the rules, how do we actually get them down to the local switch? Enter Zippy the pipeline. This separates delivery from evaluation, making sure we can distribute configurations to thousands of instances in under 5 minutes without causing an outage. Here's how it flows. Step 1, a human writes a semantic configuration, maybe using a language like JSNet in a UI to say something like, roll this out to 20% of iOS users. Step 2, the backend translates that human intent into a highly compact, machine-readable Boolean tree. Step 3, this tree is delivered asynchronously to the local SDK. And because delivery is asynchronous, if the pipeline goes down, no big deal. The local SDK just keeps evaluating using the last known snapshot. The hot path is never ever blocked by a delivery failure.
And here is the absolute secret weapon Databricks uses to hit that 10 microsecond latency. The pipeline separates dimensions into static and runtime. Static dimensions are things that literally never change for a running server, like its cloud region or its environment. Runtime dimensions, however, change per request, like a user ID. So, during delivery, the SDK pre-evaluates the Boolean tree against all the static dimensions. It basically prunes the tree down before a user ever even makes a request. That way, at runtime, the SDK only has to calculate the user ID math. It turns what could be a massive slow logic check into a lightning-fast microsecond operation. Finally, Section 5, Security and Risk Mitigation. So what happens when things go wrong? Because a system that can dynamically alter platform behavior on the fly is a prime target for attackers. A recent academic penetration test on a financial microservices environment actually found vulnerabilities tied to feature flags, with critical CVS scores ranging from 8.8 to 9.3. That is wildly high. Looking at the root causes from this chart, 33% came from inadequate access controls, 27% from misclassification of flags, 20% from poor secrets management, and 20% from a lack of audit processes. We are talking about attackers literally manipulating API-level flags to bypass one-time passwords and automated fraud detection systems. Crazy, right? So the takeaway here is that our system design must include really aggressive remediation strategies. To counter those inadequate access controls, we absolutely have to implement rigorous role-based access control, restricting write access, so say a junior dev doesn't accidentally toggle a production fraud check flag. To stop attackers from stealing insecure tokens from CI/CD pipelines, we have to mandate that API tokens are stored in secure vaults with automated rotation. And to prevent persistent backdoors, we must enforce automated scanning for shadow flags, which are basically unmonitored flags that attackers might leave behind to retain long-term access to the system. And on an operational level, we have to implement what's known as fail-static behavior. If our Zippy pipeline breaks or a core database goes offline, the local switch must never crash the app. It must always have sensible defaults, like just falling back to the original code or preserving the last known configuration. An operational kill switch must absolutely preserve its last known setting during an outage. Because think about it, if it doesn't, a simple network blip could silently re-enable a super risky feature and bring down the whole system. Which brings us to our final takeaway today. As you step back from that whiteboard, remember this quote. Feature flags aren't just toggles, they are mission-critical infrastructure. When you're designing a system to handle 300 million decisions a second, you aren't just writing basic if statements. You are building the very fabric of your application's agility and its safety. So it really begs the question, how robust is the feature flag system in your own codebase right now? Are you truly managing your flags, or are they managing you? Thanks for joining me on this explainer, and keep learning.